All right, let's go to the solutions part because you have seen some colorful drawings. Let's say we have talked about the high-level perspective, but what can we do about this? Let's come back to the main questions, the big objectives, the assessment and the mitigation. Right? I will not repeat these questions, but I'm pretty sure you still remember them. Yeah? It's about prioritization, interpretation of data, and then which measures can you take. Well, if we talk about the assessment stage, and many utilities worldwide are currently doing that because it's important. You want to map the flux or the mass of N2O in your plant under various conditions. Well, many people are now engaging in measurement campaigns, and definitely there, if you look at this, probably this tool can help a lot on helping where to measure, how long to measure, where should you put the sensor and things like that. For example, this is an example from San Colombano in Italy, a plant which our colleague Giacomo knows very well. And these people actually measured with 5 sensors in this zone here. But in fact, what you can see on the simulation, the hotspots are in a different spot. And as Ingmar has shown, these zones also shift. So it's not that this zone always has low N2O emission. It can shift. The thing is, if you have some experience with N2O, 2 years or 3 years of measurement experience, you might start seeing patterns there and you might start avoiding such things. But here's the thing, internationally, so many utilities have to start with measurement campaigns. The question is, should we really go through this trial and error based measurement campaigns? We can definitely do them very smart. So this is one point I wanted to address here. In this specific plant, this is again the top view, had to do with local concentrations and local turbulences, local mixing conditions, causing the pattern. Again, we will not go into detail, but it's very plant specific what happens. Okay, so this is the sensor location. A second part of assessment is, if you are measuring, how do you process your data and which learnings do you extract from your data? Typically, what has been done is you have a couple of sensors in the liquids phase, for example, at 1 or 2 locations. The people from Unisense are in this webinar as well. And you put them in your plant at various locations. And probably what you are going to do is correlate these measurements with other measurements you have from your plant. Dissolved oxygen, ammonia, and maybe other measurements. But what happens typically is you get this data. This is typical plant data of nitrates, of the 2 N2O sensors in this case, ammonia, DO as function of time in your plant. There are a lot of fluctuations. There are a lot of wastewater people here, so we should not explain its dynamic. But look at the locations of these sensors. So one N2O sensor was here, the second one was here. Your DO sensor to control your plant going to the SCADA system is here, and your ammonia sensor is elsewhere, and here they have a nitrate sensor. The thing is, it's very tricky. I think if you have seen these gradients and the simulations and the local conditions, it's very tricky to start correlating this data and make sense out of it. We have seen in the question of Ingmar that extrapolation to within the same plant to other conditions or extrapolations to other plants, that's a very, very big challenge. That was the biggest challenge in this poll. And this has a lot to do with it. So it's not that the measurements are not valuable, but it's very helpful if you know what's going on. So that's the assessment part, sensor location, data interpretation. If we go to the second part, the mitigation part, of course, CFD, as we have shown, is a tool that allows what-if testing, right? It's something you cannot do with any measurement. You have actually a model of your plant, and the benefit of a model is you can start playing with it. You can start testing measures. And then you can quantify how the N2O flux in your plant is in the 3D space. For example, kilograms per cubic meters per day of emission. These are typical curves we use. These are called Riemann-Nobels curves. And CFD is nice, it looks colorful, but in the end, as practitioners, as design engineers, we want to compare scenarios. And it's not so easy based on these colorful figures. What is best, what is worst? So then you have one plot and you put these N2O fluxes on one curve and you can do comparisons. So this is, for example, the fraction of a certain bioreactor volume with a certain N2O production rate. For example, this scenario 1, Ingmar has shown, this green curve, well, 10% of this reactor space, 10% has a flux higher than 20, while the other plants do not have any zones with 20 kilograms or grams per cubic meters per day. Yeah, so this is a way to how to quantify it, varying operational conditions and design conditions. Yeah, so that's the mitigation part. So yeah, what can we do? Because that's also a big debate. Many countries are building experience. We have seen that people in Denmark are, of course, very active. In the Netherlands, there is a big focus on that. UK, Australia, and many other countries are focusing on it. This is the same figure again with the 4 drivers of N2O. Well, many people, a very popular one is to look into aeration, maybe to lower the O set points. But of course, you will only do that if you don't compromise effluent quality. That's an important one. So here the question again is, if we do something about the aeration, what is the impact on the mixing? Because aeration is also mixing. And what is the impact on my effluent quality? So it's not that straightforward. On the other hand, if you're retrofitting, for example, you can do design optimizations, but in many plants, it's not easy. Or you can test other strategies, for example, alternative aeration strategies. With Air Liquide, we are now starting up 2 projects to test and compare pure oxygen versus just the regular aeration in plants when it comes to N2O. And mixing, of course, is a big topic. We have seen that over and over again. Switching on off mixers, moving a mixer has a huge impact, often underestimated. The bottom line is what we see here. It's all about minimizing the N2O production volume. So we look at N2O in a 3D perspective and see it as a big red cloud or several clouds that shift across the plant as function of your operation. And you really have to minimize the volume. So by managing transition zones, oxic, anoxic, avoiding these extreme conditions and maintaining the performance when peak loads come in. If you look a bit in the literature, our colleague Usman, for example, is doing that regularly. You have certain actions you can take. It's moderate DO levels, not too high, not too low. But yeah, of course, it's not so easy in a full-scale plant. What is not too high, what is not too low. People are playing with SRTs, so the solids retention time, COD and ratios optimal, so definitely not too low, and adequate mixing in nitrification and denitrification zones, because in both N2O can be produced and also the transition zones between them. So what we typically do is we work in steps, and one of the core purposes of this webinar was also to show that this tool is a practical engineering tool. Many people from the past experiences, like 10 years ago, think CFD is not really a practical engineering tool. The thing is, nowadays computers are very strong. We have applied this model, I think, at around 100 plants. This CFD biokinetic model, it's really a routine exercise, and you can really have first valuable results after 2 or 3 weeks in such a project, and it includes intermediate meetings and things like that. We typically apply the Pareto principle. The question is, again, do you really have to test or simulate every condition in your plant? Maybe you should start simulating the 20% of conditions that cover 80% of the time. And that will already give you a very, very good analysis, because that's phase 1, the assessment of your current plants. Yeah. Of course, along that, we also can help combining with the measurements, with the data processing and interpretation, going alongside measurement campaigns. Because don't get us wrong, the claim is not to skip measurement campaigns. We just want to provide additional insights with an additional tool to do them smarter and to also make more sense out of the data that is more generic for your future work. So these are all things we can help with in the assessment phase, and we already run multiple projects at the international scale on that. Then, of course, that's the most interesting part. When you have the model, you can start testing mitigation strategies. This is not impossible. This is not possible with measurements. For example, what if the flow rate changes? What if we reposition some mixers? It's based on this hotspot analysis that, of course, plant specifically, you will have some mitigation strategies. So it's all about what are the measures that would work. That's identification, and then you select them, and then you can test them structurally, and you don't have to always do it on site, trial and error based, because that's not easy at full scale plants. And then when you finally implement, of course, mitigation strategies, many utilities will still start measuring, of course, because you want to see the real impact of your N2O emission. still then the model is there because new insights come, it's on standby, and we can still run additional simulations to help that further. So this is a bit how we break it up. And the thing is, it can really start small, such things, and then you gradually build up because it's plant specific.